Hello, everyone, and thanks for attending this special session that we have in store for you today. Professor Branner, as you know, was our advisor for many years. We were both former 132 students and beyond. You know, he teaches a variety of classes.
Yeah.
But as part of his research group, we did some, at the time, cutting edge research in the microwave and RF arena.
Circuits.
Circuits mainly. And we're here to just give a talk, a short, very casual, what I might even call a fireside chat to you guys to see if you're interested in RF and microwaves, and also to get you excited about it. All right. So far you've seen a number of things, glimpses here and there of hardware and components and things of this nature. And what do you think about it? All right, no? Exciting or not really?
Cool.
Okay, okay, somewhat mixed reviews, right? So I do want to say a few things about what you do here in 132, right? So 132, as you know, is the RF and microwave course here at UC Davis ECE department, and it's kind of basic. Okay, you start with the basics, you start with the fundamentals, and Professor Branner, as you know, is always emphasizing the importance of the fundamentals, right? So keep that in mind, that what you're building now is the foundation for your knowledge base, right? Your knowledge base, and basically what you'll be doing is applying those concepts to whatever you're working on in the future. Okay, but 132 is not the end-all be-all of microwaves and engineering. It's really just the beginning, okay? So you see things like of this nature, and maybe to some of you it's exciting, and maybe it's not so exciting, okay? I'll just put it out there, okay? But just rest assured that there is something beyond this that is exciting and relevant to your life, all right? And what we're here to do today is to connect the dots, okay? So I like to connect the dots between what you know, what you've seen, the real world as you know it, right? And what you see in this class, okay? Know that this is the beginning of that long journey to get there, all right? So we could talk we're going to talk a little bit about ourselves. We're going to talk a little bit about the technology as it is and how it's the direction it's moving. Okay, and then feel free to ask us some questions at the end.
Yeah.
If you want to make it interactive, you can interrupt us
Yeah.
at any time too, and we could just talk about whatever questions you have. Okay, but first I would like to see here a show of hands from the audience. The students here. How many have taken 130B? Okay, good. Almost everyone has taken 130B. Okay, so you should have all taken 130B, right? Because that is the prerequisite for this class, right? And so from 130B, because I was I think Claudia also, we both did our undergraduate here as well.
Yes.
So we're very familiar with the courses here. So at the end of 130B, what was the last topic that you remember?
Antennas. Waveguides.
Waveguides. Okay, waveguides. All right, that's very good. Okay, and what is a waveguide? Are these waveguides?
Yes.
Okay, they are waveguides. Yes. Okay, so these are waveguides, and to you they're waveguides. To Claudia, they're space technology, right? But to the layman, it's just a piece of metal, right? To the layman, it's just a piece of metal, and it's difficult to see how this will fit into your life, right? Okay, but it does, right? In one way, shape, or another. Okay, it could fit into your life in class, but it also fits into your life in terms of the infrastructure around you, right? The infrastructure around you. Okay, so does anyone here know what you're learning in this course?
I hope you read the course description.
Okay, who said that? Okay, yes, gentlemen, please let me know what is 132. What does that mean to you?
It's just like an introductory course, like how to impedance match in
Okay.
RF systems and wireless communications
Okay.
and power amplifiers.
Okay.
That's why I think 132 is.
Okay, very good. So you threw out a couple terms here, a couple of technical terms of certain components that are used in wireless systems. But I thought 130A you learn impedance matching. Is that right? Did you learn the split chart? Okay, so there you go. 130A. Okay. So you will be doing some more practical hands-on stuff when it comes to impedance matching, microwave systems, and so forth. Okay. But before we begin,
How about make you remember all of this?
okay, well, it's ingrained in my DNA, I guess. Yeah, I guess so. Yeah. But yes, I do remember a lot of stuff. Yeah, I have an elephant's memory. Okay, so, but the first thing I want to talk to you guys, and I've been planning this short talk for many years, but it's never happened. What I actually want to talk to you about is your life, okay? Your life, all right? And this is not meant to discourage any of you, but I do want to talk to you about your life and where it's going to be beyond this class, okay? So, green shirt, gentlemen. Are you, what year are you?
Fourth year.
Fourth year, okay. And then what do you plan on doing after this course is over or this year is over?
Graduate school.
Graduate school, okay. And then have you thought about what graduate school you'd like to attend?
Not yet.
Look.
Here?
Yeah.
Okay, no, that's good. So is here one of your
Yeah.
options? Okay, definitely. And then beyond that, have you thought about what you want to do? Where do you want to be?
Not at all.
You never
Narrow
thought about
down
that?
this
Okay.
could go.
Okay. So exactly. So a gentleman in the burgundy shorts. Okay. Are you? What year are you? Fourth year also. Okay. And then have you thought about where you want to be after 132?
Probably workforce. Try to find a job.
Okay, try to find out. Okay, so we have an academic, right? We have an academic, and we have an industry person, right?
Well, yeah, I want to see what like the industry's like and see like what I should be learning.
Okay, no, absolutely. So absolutely, and then we have two different perspectives, both valid. Okay, both valid, but actually focused in different directions. Okay, we have an academic who will go on to become a master's student, who will work on some project, maybe write a paper or two, right? And then see what happens after that. Maybe even become a professor one day, right? And then we have another gentleman who wants to go out there and work, right? Okay, so one of the things I felt was always a little bit missing from the curriculum here, or just any curriculum in general, is actually what happens after Davis, right? What happens after UCD, right? And so this is something I think it's important to think about, especially at this stage of your school career, right? So let's do an example. Okay, let's do an example. So gentleman who wants to go to industry, okay? Name some companies that you know.
Lockheed Martin.
Lockheed Martin, okay, Lockheed Martin, very good. Okay, any other companies? Anyone else want to volunteer a company name? Okay, yes, in the cap.
Rigetti.
Rigetti.
Yeah.
Oh, Rigetti, okay, what did they work on?
Quantum computing systems.
Okay, very advanced stuff. Okay, so some kind of potentially startup-y and advanced type of system, right? Okay, something cutting edge, okay, very good. Anyone else can just throw out a random technology company name?
Keysight.
Keysight, okay, Keysight, very good. Okay, Qualcomm is another one. Okay, very good. Okay, so let's take Qualcomm. Okay, let's take Qualcomm, and I like to do this exercise here. It's a very important exercise. But let's see here. Have you ever thought about what it takes to work at Qualcomm?
Apply.
Apply. Okay, very good. Okay, apply. Okay, so let's look at RF jobs at Qualcomm. Okay, let's look really quickly. I'll load it up in a second. Not yet, but let me just find a good one. Okay. So let me just share my screen here, and let's share this. Here we go. This one. Okay, this one. Okay, there we go. Okay, so you can see the screen. Okay, so have anyone ever done this before? I encourage you. You should do this ASAP. Okay, right when you leave this class, do this exercise. Okay, go and just look up Qualcomm RF jobs. Okay, and the first thing you'll notice is a list of a bunch of terms that you may not have seen before. Okay, because you are now a student, right? So when you're in a company, the truth. No, I haven't clicked anything yet. The truth about companies is that they all have different categories and roles and names, which don't really align with your understanding of, academics, right? So they have very unique names. Okay, so let's look at this. All right, we've got System Hardware Application Senior Staff Engineer. Okay, that's quite a mouthful, right? And each one of those terms means something. Okay, we have system, we have hardware, we have application, we have staff engineer. Okay, so think about that. Okay, this one's an RF technician. Okay, so what is a technician? Okay, this one's a RF analog design internship. Okay, so what does that mean? Okay, all right. So all of these terms we've never seen. So let's look at the most advanced one here. Let's look at this one. Full time. Okay. Okay, so here we go. We've got qualifications. All right. Okay, qualifications. Okay. Qualifications. Okay, bachelor's degree in engineering, information systems, computer science, or related. So this is very general. Okay, very general. Okay. And 7 years, okay, 7 years of engineering. Okay, so you're going to run into what I call a chicken and egg problem, right? Which is everybody wants experience, right? But how do you get experience in order to get a job with experience, right? Requiring experience, right? So that is a trick. Okay, that's a tricky challenge. chicken and egg problem, right? If you can't get a job to get experience, how will you ever get experience to get the job, right? So, but look at what they ask you for, or they ask from you, and then you can kind of think about how this fits into your life. That's why this is called the life talk, okay? So let's look here, okay? So far, I haven't seen anything that pertains specifically to RF, okay? So maybe this is not the best example, but requires expert knowledge of blah, 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 okay, working independently, okay, examples, okay? So maybe what I'm actually looking for are a list of things, okay? So preferred qualifications, 12 years of hardware application engineering, okay? 2 years of work experience. So it's gonna take a long time to build experience enough to work this kind of job, okay? Now, if we look at skills, okay, this one doesn't have skills. Okay, so I'm gonna change the example now. I'm gonna look for Apple, okay? Since Apple is the biggest technology company in the world, right? So let's look at Apple. Okay, Apple, they have their own words, okay? Connectivity RF hardware design engineer. What is that, right? I don't know what that is. Wireless system validation engineer. Okay, what is that? What do you mean validation? Okay, RF system cellular. And this RF software platform development engineer. So every company has their own culture. They have their own breakdown of what things are. Okay, so let's look at RFIC, okay, because that might be one that fits into, a high performance technology, right? So let's look at this one, okay? Typically requires MS of 4 years experience or a PhD in the area of RF analog IC design with CMOS technology nodes. Okay, so each one of these keywords are important. Okay, what's CMOS? Right? What's RFIC? What's analog? Okay, here we go. RF front-end circuits, PA, LNA, mixer, oscillator, PLO, LO, VGA, filter. So you can see that in order to become proficient and serve this position, you may have to understand all of these things, right? At least to some degree, right? RFIC blocks, etc. Okay, and then we have tools here, okay? And like I said, all these terms are very foreign to you now, but it won't be in the future. Okay, we've got cadence virtuoso. Okay, so that's not even Keysight, it's cadence tools, right? Spectre RF, EMX, and similar tools, okay? So this is the kind of thing that, when you have time, sit back and browse, okay? What does this all mean here, okay? RF analog system architecture and design, systems, PHY, okay? MAC architecture and design, VLSI, RTL design, etc., 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 okay? So you can see that in order to survive as an RF engineer, there are a lot of demands. But the good thing is you get paid, right? So the good thing about a company like Apple, you get paid the big bucks, right? So if you want to live in the Bay Area, and this is another talk, right? But after you finish here from Davis, right? I assume that you want to support yourself and make a living, right? And this is the kind of thing that you'll have to seek out in order to do that. Okay, you could be paid 100K, maybe 200K, maybe even more than that, okay? Maybe up to 500K, right? So I'm just telling you real numbers from real people that I've talked with before, okay? So, but it's a long road, right? So keep this in mind, all right? And so with that, I would like to send it over to Claudia, because Claudia, where do you work now at Claudia?
I work at Boeing.
Okay.
In their space and launch division. So that includes any of their space products and defense products as well, which we can't talk too much about here.
Okay. And so Claudia has kind of certain limitations when it comes to her RF and microwave work, because that's yet another realm of technology that has its own requirements. So you've got something like defense, right, which are the companies that Claudia works at, the Boeings, the Lockheed Martins, right, the Raytheons, right, the General Dynamics, right, and then you've got the commercial industry, which is what we're looking at here, the Qualcomms and the Apples and the MediaTeks, okay, and all these other commercial companies. So somehow or another we go from this to this, okay, somehow or another, and maybe we'll show you a few more examples of that, okay, because when you see this, I also want you to keep this in mind, as this is not where these companies are in terms of their projects, right? This is just a stepping stone. RF and microwave is a very advanced and very exciting field, okay? It is not a field of old equipment, right? Sitting somewhere with waveguides, It does have waveguides, but for example, the Apple stuff does not. All right, so just keep that in mind. This is on the cutting edge, okay, when it comes to technology. All right. So Claudia, would you like to now take the realm here?
Okay.
Okay, so I'm gonna hand over to
We're going
Claudia.
To
And so we brought Claudia because she's actually a former UC Davis person. She actually has a very interesting story about how she left Davis, right, and went on her journey for a career somewhere. But please go ahead, Claudia. And the slides are very brief, but I assure you, there's a lot of content inside.
yeah. All right. So today, so a bit about me. Let me make sure you guys can see this. Okay, you guys
You
can
can
see
see
that
it.
box. Okay. So in 2008, I got my BS in electrical and computer engineering, and I studied Japanese for fun. And in 2012, I graduated with my master's under the direction of Professor Branner and Kelvin here. I did the thesis option, and I have 4 published papers at IMS, European Microwaves, and Midwest. I'm gonna get this wrong. Midwest Microwaves.
The Midwest Symposium on Circuits and Systems.
Yeah. Okay. So also in 2012, I started working at Boeing Defense, Space and Security in El Segundo, California. That's in Los Angeles. I joined their MMIC design group, Monolithic Microwave Integrated Circuit Design Groups. I started working in the lab with them, and eventually, as you prove yourself, I started doing custom IC designs. And I have ICs that are currently in orbit and in some defense applications, which again I can't really discuss here. Last year I made the switch into program management. So now I am overseeing a program, a multi-million-dollar program, which doesn't sound like a lot, but it's a good program. It's for a proprietary customer, and I oversee RF engineers. I oversee antenna engineers. I oversee my old group actually, and I have a team of mechanical engineers also who we are all working to design and develop the next generation of satellite payloads. So, these waveguides here, to me, they look gigantic. If that's any indication of the kind of technology that I'm working with.
So so you're saying there are miniaturized versions of this
Oh yeah.
that exist
Oh, yeah.
right now in the 2022
Yeah.
technology satellite going up into
Yeah.
space. Okay,
Yeah.
that's good.
Yeah.
Great. And what frequency? Well, you can't see the frequency?
Well, I can say it. It's Q-band.
Q-band, okay. And what frequency is Q-band? I'm not familiar with Q-band.
Q-band is about 50 gigahertz.
Oh, 50, okay.
Yeah,
So
40,
50
50
gigahertz,
40,
okay.
50 gigahertz, yeah.
Okay, very high.
Yeah, you'll hear a lot of satellites in like K-band, K-band, KU-band. So we're pushing a little the envelope there.
They haven't reached
Absolutely.
that table yet in the back, so tell them roughly where K-band is.
Oh, no,
Oh.
she mentioned a
Oh,
50.
you mentioned it?
K-band is like 20 to 40
Okay,
Yeah.
gigahertz.
gigahertz.
Well, okay, so I'm sorry to interrupt, but
No, everybody's free to interrupt and ask questions at any time.
No, but Professor Branner has a good point because it may be easy to kind of like box yourself in to saying, okay, a satellite operates at this band. But the truth is, there are many bands it could operate over, and it covers the entire spectrum. You can go from S band, 2 to 4 gigahertz. You could go down to L band, right, 1 to 2 gigahertz, and beyond, right. So it really depends on the application. It depends on really depends on the application, power levels, frequencies.
What orbit you're going to place your satellite in?
Exactly.
How many you're going to have?
Exactly. So these are the kind of details that are important when you have a conversation with someone about microwaves and satellites.
Okay. I think that was. Did we want to? So, Professor Branner, since you're in the room, so I included the picture of the Eiffel Tower here. Do you remember when I was delivering the first European microwaves paper?
Oh, yeah.
That whole journey. So,
You haven't heard the story yet of that one, right?
should I go into that here or?
Story.
Okay. So this was one of the first papers I was first author. I think I was first author. Was I?
I don't recall, but yeah,
Okay.
probably, yeah.
Probably. So it was in Paris, and I know I had to give my talk in the afternoon, and Professor Branner was kind enough to go there ahead of time. So I was trying to show up at the conference, but it turns out there was a bomb threat on the metro line, so I had no way to get to the conference. So I'm like running around the Louvre. I'm like trying to hail a taxi, but
Did you say running around the Louvre?
Yeah.
Okay.
The area.
Oh, okay.
Not
Not
inside.
the museum,
Yeah.
okay.
What the Louvre is?
Yeah.
Is there anyone? No, some people don't know. That's okay. Tell them what the Louvre
So
is.
it's the museum in Paris. It's a very famous museum.
What's it most famous for?
Tom
That's right,
Hanks.
yeah. The Mona Lisa. The Mona
Yeah.
Lisa.
Right?
Yeah, Da Vinci Code, or the
Yeah.
Tom Hanks,
Tom Hanks.
movie, or the Mona Lisa, where the
Yeah.
Mona Lisa's housed.
Yeah.
Yeah.
So I'm trying to find a taxi, and it's like basically my presentation's supposed to start. So Professor Branner, seeing that I haven't showed up yet, starts stalling. So he's standing up there. I don't know what you said, Professor, but you must have
Well,
stalled.
we will tell the story. The first thing was, I had gotten there early, which is, as you will find out in my case, it's kind of unusual. I got there early because I wanted to be there when Kimberly came. I wanted, here I was, the old guy, and she was going to give the first paper in the symposium.
Yeah, in that session.
In that section, and so I made it there. I took a taxi, and so the head of the chair of that session was standing around, and he was, beginning to get a little, and he asked me, he says, well, where's your presenter? And I said, well, she's coming, she's always on time, blah, 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 blah. And he said, well, and he sat there, and he was looking at his watch, he was, don't give me the floor here, guy. So he was looking, he said, well, could you get it started? And I said, well, yeah, we've been working on it together and everything, and we got version after version after version. The latest version I think I have, it's in my email, the file. And he says, oh, okay. He says, tell you what, let's get it. So he takes me out of the session, or the room where the session is, out into a large lobby area in the symposium. And he has his computer, and so he goes on board. And after a few seconds or minutes, we reach into my email and get that file out of there. And he downloads it on his computer, and away we go back to the session, right? So, but this is your lecture time, right? So. I'm in there, and we're still sitting, waiting, and no camera. He says, well, looks. I said, well, can you move our paper back to the end? He says, no, we can't do that. He's got it. Can you get started? And I could do. I had, was really up on the paper, but not in a way to present it. There's a way that, in my area, my experience, you go over the material. You go over the material for presentation, and you got it down. You just got it down. But I knew the material. But in the beginning, the introduction I did pretty well. So I started at his call to present her paper, and I kind of was doing it at a slower pace, right? Because wait. So I get past the part where I'm very comfortable, and then I start getting to the intricacies of the technical part, right? And I'm slowing. And a very important man, I've forgotten what his name is, who was doing work in that area that we know from Chalmers. You won't remember his
Angela?
name. Huh?
Not Angela, right?
It was probably Angela.
It was Angela?
And he was kind of our friend. We knew him. And he's sitting in the audience, and I see him start to, squirm around. So I had to continue to try to do my best. Oh, and I think we explained at the beginning, the presenter is going to be here. She's on her way. We know that, and she'll be here soon. But Dr. Branner will start the presentation. And so everyone knew it. But so here I am. Now I'm running out of gas in terms of really presenting this thing in a forceful way and so forth. And I noticed Angela was kind of, so the room is filled practically, and they know, everyone knows that Kimberly's supposed to present this, and I'm doing my best, right? And then in the door comes Kimberly, right?
Claudia.
Claudia. Sorry, Kimberly, stand back up. In the door comes Claudia, and I look up and I see her. I says, "Oh, the presenter, or whatever, Claudia is here." And the crowd breaks out into this massive applause, right? And to this day, I've said, "Wait a minute, was that because of my ineptness in doing this, or was it because everyone was so happy to see Claudia?" I don't know. That's a story I'll never forget. And the fact that the metro had a bomb here, and you had to get off and walk.
Did you run?
We took a taxi.
Like an episode out of 24.
Yeah, and then I ran straight in. Yeah.
So anyway, just fun stories. Fun stories. Go ahead,
But academics, as you can see, can be exciting, right?
Yes.
So for those of you who are planning to do a master's or PhD, your presenting is very critical.
Yes, you can get the school to pay for your plane ticket to a far-flung place.
Okay.
Far-off place. Yeah.
All right. Okay, so after this your master's degree experience here.
Yeah.
Yeah. So after this successful presentation of the paper, So how did you end up at Boeing?
I applied.
Okay.
Yeah, I applied online.
Okay. Were they receptive to? Were they looking for someone in particular?
I applied to several positions at Boeing, and then I'm scared to say this in the presence of Professor, but the first interview I had was over the phone, and I was so nervous. And then they asked me, "What are Maxwell's equations?" And I blanked. You didn't hear me, right? Yeah. Yeah, I blanked, and then totally failed that interview. So now it's like, well, there it goes. So I'm gonna go back on the computer, start applying to everything that I can see. And then one day I get a call from this guy at Boeing. He's like, "Hey, I'd like to hear more about you." I was like, "Okay." So I told him what I did in school, what I studied. My thesis was on GaN multipliers at the time. So I
frequency multipliers.
GaN frequency multipliers, and I went
into.
They know
all about that last lecture. We told them all about multipliers in the circuit.
Okay.
What it means and why. Go ahead.
Yes, and I went into that, and he's like, "Okay, so we'd like to fly you down and have an on-site interview." So I interviewed with I didn't know at the time there were 10 managers in the room. If I had known, I probably would have been really nervous, and I gave basically my European microwaves presentation to them.
Because by that time it was second nature, right?
Yes, yes. I was practicing that presentation so much that when I gave it to them, it was smooth sailing, and they liked me and they hired me, and I ended up in the Mimic design group, which is actually a pretty unique group because we're doing custom ICs for whatever satellite program needs them, and usually the company will come to us and say, "We need this custom IC because we can't find it commercially," or a COTS part, as we call it in the industry, a commercial off-the-shelf part. It's like, we can't find the IC that we need for this performance for our requirements, so can you guys design this? So it ends up that our designs are actually pretty challenging at times too, but we get there. Yeah.
Just to add to that, so I think Professor Branner has probably passed this around to you once or twice. Okay, so these are actually hybrid circuits, but on these little substrates here there are die, IC die. And those are the types of MMICs, RFICs that a person like Claudia or from her group would design. And these little modules can go in all sorts of systems, satellites included. But there's a high demand for designing the integrated circuits that are placed on these substrates here. And what Claudia is speaking to is that normally when you're designing a system, you could potentially pick parts out of a catalog and assemble the system using those parts. But you may come to a point where the performance demands something more customized and of higher performance. And that's where Claudia comes in and she says, "We can do it." And her group will then from scratch design that IC to meet those specifications for that system, and also make available that die for other parts of Boeing to use in their other systems. So it becomes like a mini product within the company.
Yeah. And what do we mean by design, right? So you guys have just started this, but in microwave circuits, like every shape, every bend has a meaning in this. Like, why are these waveguides here circular? Why are some of them rectangular? Why are some of them have like this triangular shape about them? Why does this, there's a big horn there on the floor, like why is it shaped like that? There's a purpose behind it, and as you'll learn in this course, you will come to understand like why you need to do things a certain way when you're designing a circuit.
And I want to add that whatever components you see here in 132, whether it be A, B, C, usually they're of a macroscopic size, right? So you can see them, you can hold them, they're very tangible. But all the concepts that go into designing those macroscopic pieces can also be miniaturized. And they could exist in different form factors, one being on a die or a substrate of this size in a very high performance microsystem. Okay, so just know that for the learning purposes, 132 will introduce you to these circuits and power dividers, filters, passives, actives, and this form that you see them in now is for introductory purposes only. There will be an application somewhere else in which it's highly integrated and of the most cutting edge technologies.
Yep. Okay.
Okay, so Claudia, you gave us an intro of how you got to where you are,
Yep.
the Mimic Design Group,
Yep.
and what you did there, and then you transitioned into program management.
Yes.
And then what was that like in terms of like what do you do in program management versus Mimic Design?
Well,
What can you say? Can you say?
No, I mean, can you be more specific what you mean by that question?
Oh, okay, so first I want to say, okay, is it natural to have gone from Mimic to program management?
Not really.
Not really, okay.
Not really. And like, why did I go into program management? I think just you won't know this now until you start working. Like you're gonna have your foundation when you graduate with your degree. You're gonna show up at a company. You're gonna do something there, and then along the way, you're still gonna be learning things. And you might find new things that you are interested in. So Kelvin earlier talked about how this class is about the fundamentals, the foundation that you are going to build your career on. And certainly for me, as I progressed through my years in the Mimic Design Group, I discovered I really enjoy the aspects of program management. And
What is program management?
So program management is you have a program, right? That means there's a customer who wants a product from you. In this case, it's a satellite payload, and they say, I need it for this use, right? And then you translate that into requirements, and those requirements become design specifications for all of your various teams. So I mentioned earlier, I have antenna team, I have mechanical engineers or product design teams, I have digital engineering teams, I have Mimic teams, and they all come together to make this one satellite payload.
Awesome.
Yeah.
And what kind of budgets are we talking about? So to design a satellite payload, which we'll get to in a second, what is a payload? Throw out a number.
Yeah, the payload is like the heart of it, right? So in
how much
terms
is
of
that?
like just the design, or
Everything, like
material
labor, material costs, everything.
So probably about 20 million.
20 million, okay, for a satellite payload.
Yeah.
Okay, good, awesome.
And
awesome.
it varies depending on the product, right?
Okay,
So if you're doing like a low Earth orbit one, kind of like what Starlink does, right? Way cheaper.
Okay,
Yeah.
okay, awesome, cool.
Yeah.
Okay, yeah,
Wait,
let's.
You said lower orbit. Can you be more specific?
Low Earth orbit, LEO,
Leos, can you be more specific about the height of those?
height
Yeah. The height, like,
300 miles.
300 miles. Okay.
Yeah.
And what is the high, just for contrast?
High.
Yeah, what's a high Earth orbit for contrast to low Earth orbit?
Well, there's HIO.
Okay, how many meters did you say?
Gosh, I don't know off the top of my head.
Okay.
But it's beyond geo.
Okay. But this is good. So you can see even in the satellite realm, there are levels to this, right? There's always levels to this.
Yes.
Right. So there's low. You're saying there's geostationary, and then there's high.
There's medium Earth orbit.
There's a medium Earth orbit, and then there's a high. Okay.
Yeah.
So and each one has
Polar
their own
orbit,
reasons, right?
Yeah.
each one has their own application, each one has their own reasons for doing things.
Correct.
So again, something to take home as homework to read about, the differences in even orbit satellites, right?
Yes.
Okay.
Okay. I think we can go to the next slide.
Part.
Huh?
Yeah.
All right. So on this slide, I included some pictures. So Boeing satellites were located in El Segundo. That's down in Los Angeles. We work both commercial and government satellite systems. So there's a link there to the company website. So on the left, I have an example of a mimic. So we've been talking about that. This is not one of our mimics. This is from some paper from Cambridge. But the principles are basically the same here. You have a die. I don't remember exactly what the size was, but typically in the die that I've designed, they've been like 2 by 4 millimeters.
So you're saying this is about 2 by 4.
This one looks pretty big. It could be
Okay.
it could be more square, like maybe a 4 by 4 millimeter.
Okay.
This looks like a PA.
Uh-huh.
Yeah.
And so for those of us who've never looked at a die like this, so what are the important features that are part of microwave design? So
Yeah,
what does it
so-
consist of, I guess?
So we'll just go around the die. So like all of these pads here,
Uh-huh.
we call them pads. They're gold. You see there's little marks on them, which means they probed them. So usually you'll have your DC connections here. There's probably a lot of ground pads. As you'll come to learn in 132, ground is very important. You need to know where your ground is. You need to have ground in all your designs.
So we've got these pads here.
Yeah.
So they're also for bonding out, right? So they're bonding out. Phone wires.
You can wire bond to them and put them into a module.
Uh-huh.
Put these die into a module. This is the RF input here.
Okay, that's the input. Okay, great,
Yep.
great.
And then this is your RF out here.
And the input and output looks like it consists of a series of 3 pads, right?
Yeah. So typically it's like ground, signal, ground. I said ground is important, right? So you have ground, signal, and ground.
Okay, very good. Yeah.
Yeah.
So this structure is kind of like it's done a certain way so that you carry the impedance from wherever the signal is coming from into the chip, so you still stay matched to 50, for example. So even the spacing, the size of the pad, the gap, the dimensions of the pad are done a specific way so that we keep like a 50 ohm match. Okay, very good.
Yeah.
And then where do we go from there?
So
From the input.
So you're branching out here.
Okay. It's divided, right?
Yeah, this is
Okay.
divided out here, and then you counted your first stage of FETs right
Okay.
here, top and bottom here.
Okay, so this is composed of FETs, okay?
Yeah.
Why did we divide out the power like that?
Yes, why did we, Calvin?
Is there a reason for that, or? Okay, well, there could be a lot of reasons for that. Yeah, there could be a lot of reasons for that. It could be for the purposes of, power handling, right? So maybe the first transistor can only handle a certain power, right? And you want.
Can I interrupt?
Yeah.
Oh, go ahead. Yeah.
Is there any way to expand that size of
Okay, let's do
Probably.
this. Yeah, let's do this.
Yeah.
Let me try to.
You can just.
Yeah, I'll do direct here. Yeah.
Zoom.
Yeah, let me just. I'll make a new slide with this. I didn't mean to stretch it out. I didn't mean to stretch it out, but yeah, this is more or less the chip. Okay.
Yeah. Okay, where
Yeah,
were we?
we can just cover we don't have to go through everything.
Yeah,
We
yeah.
just cover the features. So this
Yeah.
is transistors. There's biasing networks. What else do we have here? There's dividers, right?
Yes.
And how many stages is this?
1, 2, 3. How do you count your stages?
No, I think that's right. That's right.
Yeah.
Yeah. So.
Some people like to count them in funky ways.
Okay, let's do this. UC Davis T-shirt, gentlemen. How many transistors are there on this die?
So many.
Can you take a guess? Okay, so I'll give you a hint. Okay,
40.
you see this box, and this box, and what's in between. This is one transistor.
Yeah.
Okay. So how many would you say there are?
14.
Okay, let's see. So we have. Hold on, where's the map? Okay, we have one right here. We have one right here. Right. That's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so isn't that interesting, right? So, and if you look at them, they're actually different. Okay, look at this one. This looks longer, right, in the y direction, right, than this one, right? And even so longer than this one. Okay, so Claudia was talking about how this is a 3-stage mimic, right? So that's another parameter, right? So there's all these parameters that are not obvious, but they're there. Okay, so why does this look like this? Why? So these are actually fingers, like what we call fingers. Okay, so there's a certain number of gate fingers. And we kind of define it by how many fingers there are. Okay, so this has more fingers than this one, right? And there's more in this stage. Okay, so this is the last output stage. Okay, this is the middle stage, and this is the input stage. Okay, so why did we partition it out this way? Why didn't we make 4 stages, right? Why do we have 8 on the output? Why don't we have 12, right? So these are a lot of the questions and design choices that are made when dealing with designing the mimic and how to select certain things. Okay, so then you've selected all these transistors, then what do you do? How do you interconnect them? Right, so these are other design challenges. So you would connect them in so for example, let's look at these two. All right, so these two, the outputs are connected with this metallization here, right? So this is some kind of a combiner, right? Some combining structure, okay? One of which you may learn in 132B or C, right? Look at these two. These two are also interconnected. They're combined. Okay, but now look at the outputs of these two and these two. They are also combined, okay? You see, so there's some kind of funneling action of the combination of these transistors so that eventually it comes out to a single output. Okay, so there's this, each one has its own contribution to the performance and output of this mimic. So you can already see there's a lot of technology, there's a lot of design choices, there's a lot of know-how to produce this single item here, right? Would you like to add more to this, Claudia?
Okay, so I mentioned earlier about shapes, right? So all of these shapes have a purpose. All of these bends have a purpose. These line widths even have a purpose. This is a DC line here for the gate. Yeah.
Okay, looks
Yeah,
good. So,
yeah.
and what are the kind of specs that you've seen defined for this?
For
Yeah.
a PA.
Yeah. What are the important specs?
Well, obviously a PA, the most important is power.
Okay. Okay. Very
and then
good.
you have PAE,
Okay.
right?
And that is would be.
Power added efficiency.
Okay.
So it's the ratio of the output power to the DC power.
Uh-huh.
Yep.
And what frequencies does this operate at? Would you say?
Roughly.
Yeah. You would say so. So in your experience, it doesn't have to be this one, but your
Yeah.
experience for the satellite stuff. Well, what frequency are the mimics?
About 20.
20. Okay.
Yeah.
Okay. Very good.
Yeah.
Okay. Awesome. So we've got frequency, right? We've got efficiency. We've got output power. How about cost? Is cost a factor or not really?
Yes, it is.
It is. Okay. Absolutely.
It is. It all
Absolutely.
rolls up into your business case.
Okay. Absolutely. Okay.
So all right. So in 132, right, you're gonna learn the fundamentals behind how these devices are selected, or how these shapes come about. Like, why do I have this probably a capacitor here? Why is it there? Right. So you're gonna learn all that. Like, that's great. You're gonna be like, Professor Branner, I've completed my homework assignment. Here it is. But it's on paper. So how do you turn it into a product, right? So there's somebody that still needs, somebody, probably you, will lay this out, right? And then you'll have to fit into this die size here, your design, right? Okay, and then so great, you have a die, you're gonna send it out to a foundry. They're gonna make it for you. So typically a foundry, for this. So typically a foundry, the cost of making these, so you have to have your wafer mask. You're going to learn about mask in 132C when you make your own circuits. So in industry, when you will have a mask for each layer of this circuit, this is multi-layer here, the total cost for one of these designs for the mask will probably about 80 to 100K, and then each wafer after that can be 20 to 30K. All right, so then you have, like, each die, you chop it up from your wafer, and then you can get your per die cost. All right, and then that rolls up into somebody's bean counter spreadsheet, and then they say, all right, all right, Kelvin, your die is way too expensive. You need to
Okay.
find a way to make it cheaper, right?
Okay.
Yeah.
Okay. Then I have to resize it, make things more compact or something, right?
Yes.
And so how many design iterations would you say it takes, in your experience you've seen, that it takes to create a spec compliant part? So this is iterative, okay? It's not just a one-time deal, right?
Yeah,
you gotta
so,
do it like
so
how
sometimes
many?
you have to do it twice.
Twice? Okay,
You
okay.
might have to do it twice, and
What's the maximum you've seen?
twice.
Oh, okay,
Yeah.
that's not too bad. Okay, that's not too bad. Okay.
Yeah.
That's not too bad.
So like how are we designing these circuits, right? We're using tools. Kelvin, when he pulled up the Apple job earlier, they mentioned some simulation or CAD tools, right? So when I was doing my master's and I designed the frequency multiplier, I was working in ADS. And in ADS, it's like, okay, it's great. They have a little microstrip line, blah, blah, blah. But the real important was the modeling of this FET here, right? You don't know how it's going to behave. It's a nonlinear thing. And thanks to Kelvin's research, I used his model to create a very good frequency multiplier. And so in industry, it's the same thing. You need to have your models done correctly, and you need to be able to model this whole thing well in order to give an accurate prediction of your performance. Sometimes your models aren't that great, and then you have to iterate your design.
You bring up a good point. So this is one thing that I think is not emphasized enough in education, or just even when we discuss how to develop such an item, such a piece of technology, right? So there's circuit design that you've seen in your classes, right? But then there's this realization of that circuit into something physical, right? And fortunately and unfortunately, this is done using high performance advanced software tools, okay? So software is an integral part of designing any kind of semiconductor device. Okay, but Claudia brought up a good point in talking about models, okay? So I go into ADS and now I slap in this icon, okay? It's an icon on the page. That's supposed to represent a transistor, right? But, and if that were true, if that were taken as a given fact, then we could easily produce a predictable design, right? But the truth is that they rarely match exactly with the model, okay, the actual physical device. So then you're dealing with something that is not actually accurate. Okay, how do you produce something that will reach your design goals without actually having a correct model, right? So these are challenges. And fortunately, people are clever and they figure out ways to work around it. Testing and iterating being one of them. But this is a continual task in microwave engineering, in RFIC and MMIC design. Okay, so that's yet another area of study that can go into RFIC types of investigations. But yeah, keep that in mind. There's a lot of work that can be done here, and technology is always evolving, right? So for those of you who here is into gaming, computer gaming.
Don't
Okay,
lie.
okay, and so if you're into computer, so you must be keeping up with chips, right? You always hear AMD is coming out with like a 7 nanometer, whatever, right? Okay, so what does that all mean, right? So that means that the technology is advancing, which means these are scaling down and down in size. Transistors are getting smaller, right? And they work at higher frequencies, and so everything is evolving constantly. And so in order to keep up to date with the technology advancing, one must create more and more advanced models, right? So that the designer can then use something that's relatively predictable.
Yeah.
Okay.
And then, obviously, as you work, you will gain experience and knowledge, and you're like, okay, if I'm seeing this kind of response on the screen, probably want to move somewhere else on this Smith chart.
Okay, so we've gotten a glimpse of this, and we
Yeah.
could, like I said, we could talk about this all day long.
Yes.
But let's see what this goes into, like what kind of application this would
So I
eventually.
mentioned satellite payloads, right? This is not a satellite payload. This is a component of a satellite payload. So I'm gonna do some magic here.
Yeah.
So this next picture is really interesting. This is a commercial satellite payload. The program is O3B mPower. The customer is SES in Luxembourg. This is the fully assembled integrated product array. There are MMICs inside this. I don't think I'm allowed to say how they are integrated into this. But what you're looking at is the outside shell of the array.
How big would you say this structure is here? Is it micro scale or is it macro scale? Or
It's macro scale,
Okay.
probably about the size of this table here.
Oh, it's about the size of the table. Okay,
Yeah.
okay, very good, very good,
Yeah.
very good. Okay,
Yeah.
awesome. And you're calling this the payload, or?
Yes.
Oh, okay, okay, I
Yes.
see. Okay, awesome.
Yeah.
And what are we looking at here? Like, what is this? What
Yeah,
is this?
so I mentioned earlier, size matters, right? So there is a transmit and a receive array here, and they're at different frequencies. And the different frequencies, you can tell by the sizes.
Yeah, there's a lot of interesting shapes here. So
Yes.
again, shapes are very vital in the microwave world. So we've got this thing here, right? Looks like a circle,
Yes.
right? And then, I'm just pointing these out. I don't know the answers to these questions. If Claudia, you know the answers, feel free to chime in on what you know or can release.
Yep.
But this is circular, and this is an octagon, right? Is that right? Yeah, it's an octagon.
Yeah.
No. Yeah. Why is that?
I don't know why they made
You
it
know what?
octagon.
Okay,
No,
okay.
I don't know why.
Okay. Very good. Okay. Yeah.
Yeah.
Fair.
So,
But go ahead.
but each of those holes there, they're placed in specific positions to generate a specific radiating pattern.
Okay.
Yeah.
So you're saying that the elements. So what are these holes here? Is
So
an element?
Those are all radiating elements there.
Okay. And
Yeah.
then they will collectively, as the beam shoots out of each element, they will collectively form some kind of a shape.
Yes, form some kind of shape. Yeah.
Okay, I see.
Yeah, and then so we're not showing the waveguides that are attached here. We don't typically show those in our press photos, but there are waveguides here. So again, like you see these waveguides on a table here. I guarantee you these holes are a lot smaller than these waveguides here.
Okay, and then so I'm also seeing a lot of blank areas, but those are just capped off so that
Yeah, you don't need them.
so you get a specific pattern.
Yes.
Okay, very good.
Yep.
And how long did it take to develop this
Oh,
fine
gosh,
piece of
this
equipment here?
the whole payload. The whole payload took about 3 years.
3 years. Okay.
Yeah.
Okay. And about how big of a team would you say?
Oof. 80 to 100 people.
80 to 100 people.
Probably,
Okay.
yeah.
Okay.
One can argue like, okay, big corporation, right? You have all these inefficiencies, or you're in a startup and maybe 40 people can work on this too, right? Maybe 20 people can work on this, or maybe 1 Kelvin can work on this. Yeah.
Do I get the salary of 80 people?
Maybe we can get bought out.
Okay. Awesome. So you said this is for communications, or?
Yes.
Okay.
This is a communication satellite.
And do you know which is the transmit, which is the receive?
I'm trying to remember. I believe the receive is the bigger one.
Oh, this is the receive. Okay, I
Yeah.
see. This is
Yeah.
the transmit. Okay, so this is neat. So this goes up into space.
Yeah.
Okay, and then there's certain patterns, and this is a very sophisticated piece of antenna here. Does anyone have any questions about this particular thing? Have you ever seen anything like this before? Never. Okay, never.
Yes.
Okay, well, this is good that you're seeing something different. It almost looks like a piece of like alien technology, right? Yeah, it's kind of alien.
I think it looks really pretty.
It's pretty. It is. Absolutely.
Okay, do I have more to say on this? I don't think so. Oh, does anybody know what that blue background is about?
Well, this.
Yeah,
Is that for like RF testing?
Yeah, it
like,
is.
Quite everything else?
yeah. So this is inside an anechoic chamber. There is, I don't know if Professor Branner showed you guys, but there is one next door across the hall. And we have very, very large anechoic chambers. Like this would be like a very miniature version of it. So at my work, which is it's a factory, we actually build the satellites. It's a fully, what did one manager call it? He's very marketing about it. He said, well, we are a fully integrated facility. I was like, what the hell does that mean?
Okay, fully integrated.
Yeah.
Okay.
So he said, you can go from one end of the building and say, I want to buy a satellite that can do X, Y, and Z. And then at the other end of the building will outcome your satellite on a semi
Awesome.
trailer. Yeah.
So you pointed out something interesting here, and
Yeah.
if you haven't seen it yet, the students haven't seen it yet. Professor Branner will be introducing this material to you
Yes.
and talking about it in great detail. Okay, so when you're testing something of a wireless nature, one must do that in a specialized chamber called an anechoic chamber. And the reason for that is you want to minimize or possibly eliminate reflections of waves that are incident or coming from the device under test. And this material here along the side and the top is of this specialized foam. Okay, it's a specialized foam that essentially absorbs frequencies and signals of various power levels, okay, to prevent reflections, so that if you're sending a beam into this, let's say from off the screen directly to this unit, that beam will hit that unit, and the unit will receive energy from that beam only. That beam won't accidentally hit the back of the room, ricochet all over, and then hit the device under test. So that will give a false reading, right? We only want a very, very specific controlled experiment, right, where a beam would hit this, and vice versa. If a beam is coming out of this, we don't want that beam to be ricocheting all over. We want it to come out of the device and have a receive antenna here to receive the power coming from there, so we can analyze the signal. But this is a very special material, and I'm sure you'll see more of it in the future. 132.
Yeah. So,
And-
Professor, do you know if the anechoic chamber material you're using is flammable?
Well, we can just light on fire. See.
You can always do that.
Well, what do you say on here?
Is the anechoic chamber material you have, is it the flammable type?
Yeah, but before I say anything, I wondered what he had said.
You wanted to try to set it on fire.
Oh, set it on fire.
Test it out.
I think it most certainly is called non-flammable.
Non-flammable?
And they would
Okay.
not put it in. I will bore you enough over time to explain how they got a chamber in that building and how it passed the fire marshals and all that. So it is not supposed to be flammable.
Okay.
Okay, very good.
So little side story. At one point, Boeing was using the flammable type. And when you are sticking an entire satellite, so how big is a satellite? I think I have a picture.
Do you want to go to that?
Yeah,
next
can you,
slide?
can you show that
yeah.
picture? So this is
Going out to people so you can
yeah. So we have the payload, right? So the payload is just one part of the satellite. So you have your component, right, which is a part of your payload. Your payload is a part of the satellite. So there's other components on satellite, like your bus. You have your fuel tanks. In some cases, it's xenon. You have your star trackers. You have your gyroscopes. So all of that needs to fit in this box, and this box becomes pretty big. You can see these people down here. They're probably average size, men, or I don't know if there's any women in this picture, but they're average size people. And look at how this satellite just towers over them. And
How tall would you say, like 30 feet or something?
probably.
30 feet? Okay.
Yeah, and then and you can see that the blue material again, the anechoic chamber, in the background again. So that's how big our anechoic chamber is, and it goes up and up and up. So at some point, when we put it all together, we still want to test it before we send it out into space, because you can't just send somebody out into space and capture a satellite and repair it. So you want to make sure
Everything's done on the
you
ground
want to
first.
make sure everything works before you send it out. So a few decades ago, Boeing was using a flammable type of anechoic material, and satellites were becoming more powerful. So they were doing a test, and the RF power actually lit the anechoic chamber material on fire. And
And it'll happen.
yeah, and that happens. So this RF power, this is real stuff. You can't see it, but yeah, it's gonna light something on fire. It's gonna irradiate your body. You'll probably not want to have children or something, but
Okay.
yeah, it's actually a part of our training that there's a fire sprinkler abort button in the anechoic chamber, and
I think it's right there. No, I'm kidding.
yeah, so it's a big red button,
Okay.
and if something happens and there's a fire, like some poor soul to save the satellite has to stand there at that button to stop the sprinklers from coming out, unless everything's like catching on fire, then you should get out.
Now this is a very specialized room, right? I think there's a term for this. Do you call it high bay? Do you guys call it high bay?
Yeah, we call high bay.
High bay, yeah. So
our high bay is quite a bit bigger than this.
oh, sorry. Okay, I see. So this is
Yeah.
not even the high bay.
Yeah, that's like one
Like a low
part,
bay.
one part of the high bay.
Okay, I see.
Because there's other tests that we do, like a vibe test. We stick the whole satellite onto a vibration table and we watch it shake. There's also the noise room that you stick the whole satellite into, and it's basically a very, very loud sound system. And we blast very loud noises at the satellite, and we do that because we want to see how it survives launch on a rocket.
And these people working here with directly hands-on with the satellite, what are their roles in the engineering scheme of things? Are these test engineers?
So
or are
usually these are technicians.
Okay.
They're probably assembly and test technicians. Engineers at this stage will show up if there's a problem. But the engineers at this point have provided very good blueprint or manual of how you should be putting this together and how you should be testing it.
Okay, awesome. Yeah, awesome.
Okay.
Anyone have any questions about this
Any questions?
this image here? Anyone at all? What are these black things here?
Helix antenna? Who's that?
Is it Helix antenna?
Helix antenna?
It looks like it could be. It
Looks
looks
like
like
it,
it could be. Yeah. But yeah,
Yeah, I don't know whose satellite this is. It's one of
Okay.
our press photos.
Okay, awesome. Does it get shipped out? Okay, so I have a question.
Yeah.
So the way that it looks right now, is it just gonna float in space as it is, or is there some kind of covering on top? Like, do these cables just hang in space somewhere, or do they? Is there like a thermal material, or?
Yeah, there's thermal blankets.
Okay. I see.
It's probably more of that silvery stuff you're seeing.
Okay, so you're saying the silver stuff may eventually cover everything
Yeah.
here. Okay,
Yeah.
I see.
And then I don't think this picture or this angle is showing the wings.
Oh, there's wings. Okay.
Yeah, there's like solar power. There's all of our satellites are powered by solar,
Uh-huh.
as far as you know. And there's these wings that fold out, and we have the solar panel factory area where we like demonstrate or test how these wings will unfold in space. So it's a series of controlled explosions that unfurls the wings, and the wingspan is I think about as wide as the 737.
737.
Yeah,
Another fine Boeing product.
Yes.
Just not the Max, right?
Yeah, we won't mention the Max.
Okay, yeah. Okay, all right.
Actually, it's quite nice to fly on.
Okay.
Okay, can I have a couple more
Yeah.
questions?
Yeah.
I didn't
Yeah.
hear, maybe you did. How much, you were showing us this one satellite,
Mm-hmm.
how much power does it transmit? How much power does it receive relative?
Receive very little. Transmit it's gonna be a few kilowatts.
Watts
least.
or kilowatts?
Kilowatts.
Pulse or CW?
Sorry,
Pulse or CW?
Holster CW.
depends.
Okay, yeah, these are good questions because so you've got the satellite, right, which is floating how many miles above the Earth's surface, right?
Couple hundred.
Couple of hundred. Okay, so there's some kind of a ground station, right, that's sending a signal up to here, right? By the time it hits the satellite, it is dissipated, by orders of magnitude, right? But luckily, a microwave design engineer like yourselves will have worked on this satellite, and you know how we can compensate for that, right? So what would you say is the first component here that we'll use after we've received this tiny signal? Preamplifier? Okay, some kind of preamplifier, okay? Some kind of preamplifier. Now, the problem with that is, what is the key parameter that gives that amplifier the appropriate performance, okay? So because we've got all these signals hanging around in space, we've got all this stuff basically that we don't want going into the satellite, and so potentially that gives rise to noise, right? Noise, right? And of course of the satellite itself even, right? So the type of amplifier that would be designed in that case is called a low noise amplifier, which has its own art in terms of designing. But the LNA, which is the first device after the antenna, will be responsible for boosting that signal and giving this enough signal basically to operate. And that is also another exciting area of RF and microwave design. And hopefully Professor Branner, if you stick around to 132C, okay, he will talk about noise and low noise amplifier design. He may even go to the low noise amplifier design lab if it comes around to that ever again. But there's a lot of exciting material in here. Amplifiers which transmit, low noise amplifiers which receive and boost the signal, and everything in between when it comes to a microwave receiver. The mixers, the power dividers, the phase shifters, the filters, etc.
So wait a minute, the antennas, you didn't say much about.
Oh, okay. Well, that's not my particular field of expertise,
Yeah.
but
I
but
gotta
we
say,
have
that's not
Peng.
really mine either.
Yeah, but we have Peng. Yeah, we have Peng to talk about antennas, but and you can ask him offline.
Yeah.
Right now it's I think we're at 6.
Okay.
And so I don't know if you want to do any more, Professor Branner, but I just wanted to respect the time.
Well, maybe we should ask them for questions.
Okay, sure, yeah. Okay,
Okay,
if you have
sure.
any questions.
So do people in your projects, or do you know of RF projects that go on where there's a lot of programming involved, like using C or Python or anything?
Yeah, so these payloads, I've only been talking about the analog. There's also a digital aspect to it. There are ASICs, there are FPGAs in the back end that is processing all this data as well. So this not necessarily like Python, but there is some programming involved.
I would say for any of these signal processing chains, there is always going to be a lot of programming, a lot of DSP, a lot of programming. Now, what kind of programming? That's another story. But there are controllers all over this thing, right? Digitally controlled, components all over. So programming, in my opinion, is always something that is one should be strong in if you're going to go into this avenue here. You don't necessarily have to get a job as a DSP signal programmer, but to be familiar with it is always helpful. But yeah, it's a very exciting area if you're talking about programming and signal processing and what we call software-defined radio. You have kind of software to define microwave and RF components and processing. So yeah, programming is important if you're looking into that.
Okay, could we get another question? Anyone have another question?
Yeah, go ahead. Yeah.
Yeah, how big is the chip you're talking about?
Which one?
The first chip, the first
Oh, the
picture you
Mimic?
mentioned? Yeah.
So that wasn't my design. I'm guessing it's a 4x4 millimeter.
What was that?
4x4 millimeter. That's my guess. It's not my design. It's something I pulled from the internet.
Okay.
Yeah.
So chips, right? The size can vary wildly. You could vary wildly. You could go from half a millimeter by half a millimeter, and up from there. So it really depends on the application, the technology, and basically the circuit that's on there. But it could get very small. It could get very small, even fractional millimeter squared. Yeah. So it really depends. So if you're really interested, what I would say is go to some Mimic company website and just click on their data sheet. It'll tell you right away what the size is. Okay. Usually, if you go to a Qualcomm or something, or someone like that.
Any other questions? Next question.
Do you get to see the projects you manage?
Do I get to see them?
Did they get
Yeah,
to
like
see-
before they got sold or shipped out or
Oh,
assembled.
no, not always. I think now that I'm in program management, I do get to see more of it though. Because back when I was in the Mimic group, I was basically just focused on that component of the payload, and I rarely got to see beyond that.
Question.
Wait, another question. Did you have a question?
Yeah. How much money do y'all bank?
Huh?
How much money do y'all bank?
How much money do you all bank?
Oh, do we all bank?
So what is a profit margin? Let's put it that way.
Profit margin.
Yeah. Let's say a customer comes to you and says, "I want to build a satellite." You told them 20 million, like earlier. Like what?
Well, that's just to develop it. I didn't
Okay.
say anything about launching it.
Okay, all right. So let's add
I
that
didn't
on
say
top
anything
of it.
about integration, right? So
Okay, just mentally, just give us a
so-
rough clue.
so
Like, what is the profit?
let's say probably a couple million each.
Okay, so let's say
Yeah.
so let's say that's something like a what? 20%? Would you say 20% profit?
20% would be pretty good.
Okay,
Yeah.
20%. There you go. Of course, it's a very loaded question, right? It could depend on, how many launches, right? What kind of deal you have with the
what
company.
kind of vehicle you're going to
Yeah,
use?
what
Are you
kind of
going to use a
long-term-
Falcon 9? Or are you going to use an SLS?
Where are you launching? Can you say us where are you launching?
So it depends on the program, Professor. So if it's a commercial, you can use any commercial launch site. Sometimes, well, maybe not anymore. Like Ukraine was one of them. But if it's a government, it usually would launch from a Space Force base.
How about any on the sea or any?
I don't think we're doing sea launches anymore. That was a thing at some point where we would do a sea launch. Have you guys seen For All Mankind on Apple TV Plus? They launched this like rocket from underneath the water in the ocean,
Oh,
which is
yeah.
totally unrealistic. Because like, why would you stick a rocket and like a sensitive electronic device in salt water?
What does a nuclear submarine has to launch the warhead from underneath the water though?
Yeah,
They do that, yes.
yeah.
But it's not a satellite, right?
Yeah, it's not a satellite.
warhead, yeah, it's a warhead, yeah.
It's meant to go destroy something.
Yeah, it's a little different, yeah. Yeah, we're not familiar with that
Yeah.
territory, but I would surmise it's quite a bit different, yeah. Quite a bit different.
Okay, well, if you have some other questions, hang around and feel free to approach them and ask them. Otherwise, I will officially dismiss class. Okay.
All right, thanks for
Alright,
coming.
yeah. Thank you, and feel free to. And again, if you have any questions for Claudia or me, just talk to us,
Yeah,
as soon as.
we'll be here.
Yeah, we'll be here for a little bit longer. Okay, thank you, everyone.
Thank you.